What if the most dangerous shift in our world isn't a single event, but a quiet change in the baseline that makes extreme events feel ordinary? We are used to thinking about disasters as isolated moments. A storm makes landfall, a heat wave breaks records, a system fails, and then, eventually, everything resets. That mental model is comforting because it implies recovery, implies a return to normal. But what if the concept of normal itself is no longer stable? For decades, scientists and engineers relied on historical patterns to define risk. Storm seasons had boundaries, infrastructure had thresholds, and statistical models translated past observations into future expectations. This framework worked not because it was perfect, but because the underlying system behaved within a relatively stable range. Variations existed, but they oscillated around a predictable center. Now imagine that center slowly shifting, not dramatically enough to trigger immediate alarm, but steadily enough that each new data point begins to stretch the limits of what was previously considered rare. A storm that forms slightly earlier than expected, a temperature that exceeds seasonal norms by a small margin, a pattern that doesn't quite fit but isn't yet extreme enough to redefine the rules. Individually, these anomalies are easy to dismiss. Weather has always been variable, and outliers have always existed. But when those outliers begin to cluster across different systems and regions, they start to challenge the assumption that the baseline is fixed. The question is no longer, why did this one event happen? But why are the conditions that allow such events becoming more common? This is where perception becomes unreliable. Human cognition is tuned to notice sudden change, not gradual drift. We react to spikes, not slopes. So when the system shifts slowly, we continue to interpret events through an outdated lens, assuming that what we are seeing is still within the bounds of normal variation. But if the baseline has already moved, then the definition of extreme has moved with it. And what we are calling unusual may in fact be the early expression of a new pattern that has not yet been fully recognized. And once that baseline begins to shift, the tools we rely on to interpret reality start to lose their precision. The frameworks that once explained most extreme events were built around a simple idea that variability follows patterns. In climate science, one of the most influential of these patterns is the oscillation between phases that either enhance or suppress activity across entire regions. For years, this acted like a master dial. When activity increased, we looked to the dial for explanation. When it decreased, we did the same. It gave us a sense that even the most chaotic systems were still governed by something predictable. But a pattern can only explain variation relative to a stable reference point. If that reference point begins to move, the pattern does not disappear. It simply becomes less informative about the extremes. A neutral state that once implied moderation can begin to produce outcomes that would have previously required a strong push from the system. In other words, the relationship still exists, but its meaning changes. This creates a subtle but critical problem. The models are not failing in a technical sense. They are still correctly identifying relative conditions. What they struggle with is the absolute scale of what those conditions can now produce. A moderate signal layered on top of a higher baseline can generate results that exceed historical expectations without violating any of the underlying rules. Think of it as a system that has not become more chaotic but more amplified. The same inputs now lead to stronger outputs because the environment in which those inputs operate contains more energy. Warmer oceans store more heat. The atmosphere holds more moisture, and the thresholds required for rapid intensification are reached more easily and more often. This is why certain events feel surprising even when they follow known physics. They are not breaking the rules, they are exposing the limits of how those rules were applied in the past. The system is behaving consistently, but the context has changed. And that shift in context is enough to push outcomes beyond what older frameworks were designed to anticipate. At this point, the question evolves again. It is no longer just about whether extreme events are increasing, but about whether our definitions of normal, moderate, and extreme still correspond to the reality unfolding around us, or whether we are measuring a new world with outdated scales. And when those outdated scales persist, they begin to distort not just our forecasts, but our sense of timing. For most of modern history, seasons acted as reliable boundaries. Not perfect, but dependable enough that societies could organize around them. There was a time for preparation and a time for relative calm. Storm activity followed recognizable windows, and outside those windows, the probability of extreme events dropped sharply. That predictability became embedded in everything, from insurance models to construction schedules to emergency planning. But seasonal boundaries are not physical barriers. They are statistical summaries of past behavior. When the underlying conditions shift, those summaries begin to blur. Warmer ocean surfaces reach critical thresholds earlier in the year. Atmospheric conditions that once aligned briefly now persist longer. The result is not just stronger events, but a widening of the window in which those events can occur. At first, this expansion is subtle. An early storm here, a late season anomaly there. Each instance can be explained away as unusual but not unprecedented. Yet over time, the edges of the season stretch further apart, and what used to be considered off-season begins to host events that no longer feel like exceptions. This is often described as season creep, but the term understates what is happening. It is not simply that the calendar is shifting, it is that the distribution of risk is flattening across time. Instead of a sharp peak surrounded by low probability margins, the curve begins to spread. High-impact events are no longer confined to a narrow band, but can emerge across a broader portion of the year. That change carries consequences that are easy to overlook. Systems designed around seasonal downtime lose their buffer. Maintenance windows shrink. Resources that were once rotated or rested between peak periods are now under more continuous demand. Emergency response structures that relied on predictable surges must now operate under the possibility of sustained pressure. And for individuals, the psychological effect is just as significant. The expectation of a safe period erodes. The sense that risk can be temporarily set aside becomes harder to justify. Instead of preparing for a defined season, communities begin to exist in a state of low-level readiness that never fully resolves. This is where the earlier shift in baseline and the limitations of traditional frameworks begin to converge. A higher energy system does not just produce stronger events. It redistributes when those events are possible. The calendar, once a useful guide, becomes less reliable as an indicator of safety. And when timing becomes uncertain, another assumption starts to weaken as well. The idea that events will remain isolated from one another, rather than beginning to overlap in ways that strain the systems built to handle them. And once events begin to overlap, the problem is no longer intensity or timing in isolation, but interaction. In a lower energy system, extreme events were more likely to occur as separate incidents. A storm would pass, recovery would begin, and only after a period of stabilization would the next disruption arrive. This pacing created a natural buffer that allowed infrastructure, institutions, and communities to absorb shocks and gradually return to baseline conditions. But when the frequency of extremes increases and the seasonal window expands, the probability of overlap rises sharply. Not because the events are connected in a direct causal sense, but because there are simply more of them occurring within a given time frame. Statistically, the more often you roll the dice, the more likely you are to see combinations that once seemed rare. This is where a common misunderstanding emerges. When multiple disasters unfold in close proximity, the instinct is to assume they must be linked. A storm, a heat wave, a flood, all appearing within days of each other, feels like coordination. But in many cases, the connection is not causal, it is conditional. Each event is driven by its own mechanisms, yet all are enabled by the same elevated background state. A warmer atmosphere holds more moisture, increasing the potential for intense rainfall. Higher ocean temperatures provide more energy for storms. Altered temperature gradients can influence jet stream behavior, shaping the conditions for severe weather outbreaks. These processes operate independently, but they are all drawing from the same underlying reservoir of energy. As that reservoir grows, the system does not just produce stronger individual events, it produces more opportunities for those events to coincide. And when they do, the effects are not additive, they are compounding. Consider what happens when a region experiences heavy rainfall on already saturated ground. The impact is not simply the sum of two rain events. It is a shift from manageable runoff to widespread flooding. Or, when extreme heat coincides with peak energy demand, pushing electrical grids beyond capacity. Or, when a major storm strikes a community still recovering from a previous disaster, where infrastructure is weakened and resources are already depleted. These overlaps expose a limitation in how risk has traditionally been calculated. Most systems are designed around single event scenarios: a maximum wind speed, a peak flood level, a worst case temperature. They assume that extreme conditions will occur independently, allowing each system to be optimized for a specific type of stress. But reality is increasingly violating that assumption. The stressors are stacking. A drainage system designed for heavy rainfall may fail not because the rainfall exceeds its design limits in isolation, but because it arrives on top of prior conditions the system was never meant to handle. A power grid may collapse not from a single surge in demand, but from sustained pressure combined with environmental stress that reduces efficiency. This shift from isolated extremes to interacting extremes represents a fundamental change in how risk manifests. It is not just that events are becoming more severe or more frequent. It is that they are beginning to intersect in ways that amplify their impact beyond what traditional models account for. And as these intersections become more common, another constraint begins to emerge. One that is less about the environment itself and more about the systems we rely on to respond to it. The capacity to recover before the next disruption arrives. And when recovery can no longer keep pace with disruption, the system enters a different kind of stress entirely. Up to this point, most models assume that after an extreme event, there is a period of stabilization. Damage is assessed, repairs are made, resources are replenished, and systems gradually return to functional capacity. This recovery phase is not optional. It is built into how resilience is defined. The ability to absorb a shock depends on having time to rebuild before the next one arrives. But as the interval between events shortens, that assumption begins to fail. The recovery phase does not disappear, it becomes incomplete. Repairs are made, but not to the original standard. Temporary solutions remain in place longer than intended. Infrastructure is restored to operational status, but not fully reinforced. Each cycle ends with systems that are functional yet still carrying residual vulnerability. This creates a compounding effect. When the next event occurs, it does not strike a fully recovered system. It strikes one that is already weakened. The damage is therefore not just a function of the new event's intensity, but of the accumulated deficits left behind by previous ones. Over time, this leads to what can be described as a recovery gap. The duration required to fully rebuild exceeds the time available between disruptions. The result is a permanent state of partial recovery, where systems are continuously in the process of being fixed but never fully restored. This dynamic is particularly visible in infrastructure, where rebuilding is constrained by cost, logistics, and time. Strengthening a structure to withstand more extreme conditions requires more materials, more labor, and more complex design. It cannot be done instantly, and it cannot be done everywhere at once. Prioritization becomes unavoidable. Critical systems are addressed first: hospitals, power networks, emergency facilities, while less visible or less immediate needs are deferred. Residential buildings, secondary infrastructure, and long-term upgrades are pushed into the future. But when the next event arrives, before those upgrades are completed, the deferred vulnerabilities are exposed again. The financial dimension reinforces this cycle. Each recovery effort draws on limited resources, and repeated disruptions reduce the capacity to invest in long-term resilience. Funds that could have been used to strengthen systems are instead used to restore basic functionality. The focus shifts from improvement to survival. At the same time, the human dimension becomes harder to quantify but equally significant. Repeated cycles of disruption and incomplete recovery erode confidence in the stability of the environment. Decision-making becomes more reactive, less strategic. Communities adapt, but they adapt to instability rather than to a stable new equilibrium. What emerges is not a system that has adjusted to a higher level of risk, but one that is gradually losing its ability to fully reset. Each event leaves behind a trace that is not entirely removed before the next one arrives. And as those traces accumulate, the baseline condition of the system begins to degrade. This is the point where resilience, as traditionally defined, starts to lose meaning. Not because systems cannot respond, but because the concept of returning to a prior state becomes less attainable. The goal shifts, often implicitly, from full recovery to maintaining continuity under persistent stress. And as that shift takes hold, another question begins to surface. Not just how systems fail under pressure, but how our understanding of those failures is shaped by the way we interpret the information surrounding them. And as pressure builds within the system, the way we interpret what is happening becomes a variable in itself. Human perception was never designed to process slow structural change combined with intermittent extremes. It is highly sensitive to sudden events, but far less responsive to gradual shifts in baseline conditions. This creates a gap between what is actually changing and what feels like it is changing. When multiple disruptions occur close together, that gap is filled by instinct. We look for patterns, connections, causes that tie everything into a coherent narrative. This tendency is useful in many contexts, but under conditions of increasing complexity, it can become misleading. Independent events begin to feel coordinated simply because they occur within the same window of attention. At the same time, the modern information environment amplifies this effect. Events that would once have been experienced separately are now presented simultaneously. A storm in one region, a heat wave in another, flooding somewhere else, all appear in the same stream of information. The brain processes them as a single cluster, even when the underlying mechanisms are unrelated. This does not mean the perception is entirely false. As the system produces more extreme events, real overlaps do become more common. But distinguishing between coincidence and meaningful correlation becomes increasingly difficult. The signal is real, but it is embedded in noise that is equally real. In this context, simplified explanations gain traction. Narratives that reduce complexity into a single cause or a single actor are easier to process than those that require holding multiple variables in mind at once. They offer clarity, even if that clarity comes at the cost of accuracy. The challenge is that accurate explanations often lack immediacy. They depend on understanding probabilities, feedback loops, and gradual shifts that do not produce a single moment of revelation. Instead, they accumulate over time, requiring sustained attention to recognize. This creates a tension between what is easy to believe and what is necessary to understand. The more complex the system becomes, the more effort is required to interpret it correctly. And under stress, whether from repeated disruptions or from information overload, that effort becomes harder to sustain. As a result, responses can diverge. Some interpretations overconnect events, attributing them to a unified cause that does not exist. Others underconnect, dismissing patterns as coincidence and failing to recognize emerging trends. Both responses reduce the ability to adapt effectively because both are based on incomplete readings of the system. What is required instead is a different kind of attention, one that can separate independent events from shared conditions while still recognizing that those conditions are shifting. This means accepting that multiple things can be true at once. Events can be unrelated in mechanism, yet connected in probability because they arise from the same elevated baseline. Maintaining that distinction is difficult, but it becomes essential as the system continues to evolve. Because the way we interpret these patterns influences how we prepare, how we allocate resources, and how we respond when the next disruption arrives. And if interpretation shapes response, then the final question is not just how the system behaves, but whether the frameworks we use to understand it can keep pace with the reality they are meant to describe, or whether they too begin to fall behind, leaving us navigating a changing world with models that no longer fully apply. And if those frameworks begin to fall behind, the consequences extend beyond interpretation into the physical systems we depend on. Every piece of infrastructure is built on an assumption about the future. Not explicitly, but mathematically. Engineers take historical data, define a range of expected conditions, and design systems that can withstand those limits with a margin of safety. The result is not a structure built for uncertainty, but one calibrated to a specific understanding of risk. This approach works when the underlying conditions remain stable. A bridge designed for a certain range of loads performs reliably if those loads do not change significantly. A drainage system manages runoff if rainfall stays within projected intensities. A power grid balances supply and demand if temperature and usage patterns follow predictable curves. But when the baseline shifts, the assumptions embedded in those designs begin to diverge from reality. The infrastructure does not suddenly become defective. It continues to operate exactly as it was designed to. The problem is that the conditions it was designed for are no longer the conditions it is experiencing. This creates a form of failure that is often misunderstood. It is not caused by poor construction or inadequate engineering. It is caused by a mismatch between past data and present conditions. The system is correct within its original parameters, but those parameters are no longer sufficient. Consider how this plays out across different domains. Electrical systems are rated for specific temperature ranges. As ambient temperatures rise beyond those ranges more frequently, components operate less efficiently and degrade faster. At the same time, demand increases, placing additional stress on systems already operating near their limits. Water management systems are designed based on historical rainfall distributions. When precipitation patterns shift toward more intense events, the capacity of those systems is exceeded not because they were undersized at the time of construction, but because the definition of a typical event has changed. Coastal defenses rely on historical sea levels and storm surge data. As baseline sea levels rise and storms produce higher surges, barriers that once provided adequate protection are overtopped. The design has not failed in a technical sense, but the environment it was built to resist has evolved. Across all of these examples, a common pattern emerges. The gap between design conditions and actual conditions widens over time. Closing that gap requires updating not just individual structures, but the entire framework that determines how those structures are planned and built. This is where the challenge becomes systemic. Updating infrastructure is not simply a matter of repair. It involves revising standards, reallocating resources, and committing to long-term investments that account for conditions that are still changing. It requires building for a future that cannot be defined with the same certainty as the past. And time becomes a limiting factor. Large-scale infrastructure projects take years to complete. Supply chains, labor availability, regulatory processes, and funding cycles all impose constraints. Even under ideal conditions, adaptation lags behind change. When disruptions occur faster than systems can be updated, the gap persists. Each event tests structures that are already partially outdated. Each recovery effort restores functionality, but often without fully addressing the underlying mismatch. This leads to a gradual shift in how infrastructure functions within the system. Instead of acting as a stable foundation that absorbs variability, it becomes another layer of vulnerability, sensitive to conditions it was not designed to handle. And as this sensitivity increases, the question is no longer just whether systems can withstand individual stresses, but whether the combined pressure of environmental change and structural lag will continue to widen the gap between what is built and what is required, or whether something will intervene before that divergence becomes irreversible. And if that divergence continues to widen, the final constraint is not physical but systemic in a broader sense. Because infrastructure, perception, and environment do not operate independently. They form a feedback loop. A system produces stress. Infrastructure absorbs part of that stress. Perception interprets the outcome, and those interpretations shape the next set of decisions. When each layer begins to drift out of alignment, the feedback loop itself becomes unstable. In a stable system, feedback helps maintain balance. Signals are clear, responses are proportional, and adjustments bring conditions back within expected ranges. But when the baseline shifts and the frameworks lag behind, the signals become distorted. Events appear more sudden than they are. Risks seem either exaggerated or underestimated depending on the lens applied. And responses begin to oscillate between overreaction and delay. This is where uncertainty compounds. Not just uncertainty about what will happen, but uncertainty about how to interpret what is already happening. Decision-making becomes more complex because the reference points used to guide those decisions are no longer reliable. For example, a system may appear to recover after an event, restoring power, clearing roads, reopening services. From a surface perspective, functionality has returned. But if the underlying vulnerabilities remain, if the infrastructure has not been fundamentally updated, then what appears to be recovery is actually a temporary stabilization within a degraded state. This distinction is difficult to maintain over time. As long as systems continue to function, even at reduced capacity, there is a tendency to treat that functionality as evidence that the existing approach is sufficient. Incremental fixes are favored because they are faster and less disruptive. Long-term restructuring is delayed because its necessity is not immediately visible. At the same time, the cost of adaptation increases, not only in financial terms, but in coordination. Updating one system in isolation is rarely enough. Power grids depend on fuel supply chains. Water systems depend on energy. Emergency response depends on communication networks. Each component is interconnected, and strengthening one without addressing the others can create new imbalances. This interconnectedness means that adaptation is not a single decision, but a series of coordinated changes across multiple layers. And coordination requires time, alignment of priorities, and a shared understanding of the problem, all of which become harder to achieve as uncertainty grows. Meanwhile, the system itself continues to evolve. The baseline does not pause while decisions are being made. The conditions continue to shift, sometimes gradually, sometimes in sudden jumps that reset expectations again. This creates a moving target problem. By the time a solution is implemented, the conditions it was designed for may have already changed. The gap narrows briefly, then begins to widen again. Adaptation becomes a continuous process rather than a finite goal. At this stage, the challenge is no longer framed in terms of preventing failure or ensuring stability in the traditional sense. It becomes a question of whether the system can maintain coherence under persistent change. Whether its components, physical, institutional, and cognitive, can remain sufficiently aligned to function effectively despite the shifting baseline. And that leads to a deeper tension. Because maintaining coherence requires agreement on what the system is responding to. It requires recognizing that the baseline has moved, that the frameworks need updating, and that the cost of delay increases over time. But agreement itself is part of the system, influenced by perception, information, and the same uncertainties that complicate the physical response. So the question is no longer just about how the environment will change or how infrastructure will adapt, but whether the systems that interpret, decide, and act can evolve quickly enough to keep pace with the conditions they are trying to manage, or whether that gap will continue to expand in ways that are only fully visible once the consequences are already unfolding. And if that gap continues to expand, the final shift is not in the system itself, but in how we define stability. For most of modern history, stability implied predictability. A system was considered stable if its behavior remained within known bounds, if its extremes were rare and its averages consistent. Planning depended on that assumption. You could model the future because the past provided a reliable template. But when the baseline moves continuously, stability no longer means returning to a fixed state. It begins to mean something closer to persistence under change. The system does not settle, it adapts in motion. And that introduces a fundamental contradiction. Because the structures we rely on, physical, institutional, and cognitive, are optimized for fixed targets, not shifting ones. This contradiction becomes most visible at the edges, not in everyday conditions, but in the moments when systems are pushed beyond their expected limits. When a storm exceeds design thresholds, when demand surpasses capacity, when recovery timelines collapse into each other, these are not isolated failures. They are points where the underlying assumptions are exposed. And once exposed, those assumptions cannot be easily reinstated. You cannot unsee the mismatch between what was expected and what occurred. The next decision is made with that knowledge in mind, but without a fully developed alternative framework to replace it. This creates a transitional state. The old models are no longer sufficient, but the new models are not yet fully formed. Decisions are made in that gap, using partial information, revised expectations, and a growing awareness that certainty itself is becoming less accessible. At the same time, the system continues to produce signals. More data, more events, more evidence of how conditions are evolving. But data alone does not resolve the uncertainty. It must be interpreted, integrated, and translated into action. And that process takes time. Often, more time than the system allows. So adaptation becomes uneven. Some areas adjust quickly, incorporating new information and updating their responses. Others lag behind, constrained by resources, by institutional inertia, or by the difficulty of abandoning established frameworks. The result is not a uniform transition, but a fragmented one, where different parts of the system operate under different assumptions simultaneously. This fragmentation introduces another layer of risk, not because any single part fails completely, but because the lack of alignment reduces overall coherence. Systems that depend on coordination begin to experience friction. Responses become less synchronized. The margin for error narrows. And within that narrowing margin, small discrepancies can produce outsized effects. A delay in recognizing a threshold, a misinterpretation of a signal, a decision based on outdated assumptions. Each on its own may seem minor, but within a tightly coupled system, they can cascade. Which brings the trajectory back into focus, not as a series of events, but as a continuous process of divergence and adjustment. A system moving away from the conditions it was built around, while the mechanisms designed to manage it attempt to follow. The question is not whether adaptation will occur, it already is. The question is whether it can occur fast enough, consistently enough, and coherently enough to keep the system functional as the baseline continues to shift. Because if stability no longer means returning to what was, and adaptation never fully catches up to what is, then the system exists in a state that is neither stable nor unstable in the traditional sense. It continues to operate, to respond, to adjust, but without ever fully resolving the gap between expectation and reality. And if that gap is not closing, but simply moving, then the problem is no longer where the system will settle, but whether it ever does. And if it never does, then what we are left with is not a temporary transition, but a permanent condition of drift. In that condition, the question changes one final time. It is no longer about predicting specific events or even defining new thresholds. It becomes a question of orientation. How do you navigate a system where the reference points themselves are moving? Where every measurement is relative to a baseline that is no longer fixed? Because prediction depends on stability, It requires that relationships between variables remain consistent enough to project forward. But when those relationships begin to stretch, when inputs produce outputs that exceed prior expectations, prediction starts to lose resolution. Not entirely, but enough that the margin of error grows wider with each step into the future. This does not mean the system becomes unknowable. The physics still apply. The processes are still governed by the same underlying rules, but the range of possible outcomes expands. And with it, the difficulty of choosing a single path with confidence. So decisions shift from optimization to hedging. Instead of asking what is most likely, the focus turns to what is possible. Instead of designing for a defined maximum, systems must account for a spectrum of extremes that continues to evolve. This introduces a different kind of burden, not just on infrastructure or institutions, but on cognition itself. Because navigating uncertainty at this scale requires holding multiple possibilities in mind at once, without collapsing them into a single narrative. It requires accepting that outcomes may fall outside familiar categories, that events may not conform to expectations even when the underlying processes are understood. And that tension does not resolve easily. The need for clarity pushes towards simplification. The reality of the system resists it. The more the system shifts, the more uncomfortable that gap becomes. At the same time, the feedback loop continues. New events provide new data. That data reshapes interpretation. Interpretation influences response, and response in turn alters how the system is experienced, if not how it behaves. But there is no clear endpoint to this cycle. No moment where the system announces that it has reached a new equilibrium and can once again be treated as stable. Instead, there is only a continuous adjustment, a recalibration that never fully completes. And within that ongoing recalibration, a subtle question begins to emerge. Not about the system alone, but about the observer within it. Because every model, every framework, every attempt to understand what is happening is constructed from a particular vantage point. A set of assumptions about how the world behaves, what counts as normal, what defines an outlier. If those assumptions were formed under conditions that no longer exist, then the act of observation itself carries a form of lag. We are measuring a moving system with tools that were calibrated in a different state, updating them as we go, but never quite fast enough to eliminate the gap entirely. So the question remains open, not just in terms of what the system will do next, but in how we will recognize it when it does. Whether the patterns we think we see are signals of a new structure forming or reflections of an old structure that has already begun to fade.